Okay, so last time, I'm sorry, I have a couple of pieces of business we need to deal with first. Every year, George Rice, some of you have had him for class, arranges, a lot of us are involved in the driving, but arranges a tour up at CSI, Computer Services in Paducah. If you haven't been, I would recommend going. CSI is a company based in Paducah. They do backroom services for banks, but they've gotten a lot bigger than that. They do completely managed networks, all of that sort of stuff. They're in 40 states. They are the largest business of that type in the country, and they are an extremely well-run organization. Their network is fascinating. It's huge, and we get a tour that's a whole lot better than, they almost don't do public tours. So we get a very good tour. They are the largest employer of TSM graduates that we have. We've got, gosh, I couldn't tell you how many people we have working up there, particularly in their network and security, and they still run a division called telecommunications, which is their wide area net layer 2 stuff, basically. If you can go, I would recommend it to you. I'll get a sign-up sheet up, or an announcement up on Canvas. You do need to let us know if you're going ahead, because we have to arrange transportation. It's going to be the Tuesday before Thanksgiving. Our tour up there is from 1 till about 3 in the afternoon. We'll provide transportation from here, or if it's more convenient for you, you can meet us up there and then head on home for Thanksgiving, whatever. So anyway, I'll have more stuff up on the front from that. Okay, so last time we started looking at 802.11 networks. Kind of went through the view from 30,000 feet. And what I want to do is start looking at some practical considerations of that. Between now and the end of the semester, we're going to take it apart, kind of look at various aspects. The first thing I want to be sure you get is to see how to apply a lot of this stuff we've talked about in thinking about these networks. There is, with anything that's widely accepted, you get a lot of rules of thumb that don't make sense, and you have some rules of thumb that do make sense. And I'm going to try to separate those for you. This is a slide actually I showed you last time. I brought it back up so we can talk about it. 802.11 networks actually operate in 2 frequency bands. We have the more commonly used one right now is the 2.4 gigahertz allocation that you saw, you're probably familiar with from using 802.11g. 802.11n is the current protocol. We're actually going to kind of jump into that pretty quickly. For today, I'm staying kind of protocol agnostic. For today, I really don't care about which protocol we're talking about. Most commonly right now, you're using the 2.4 gigahertz spectrum, and the way it's laid out, there are only 3 channels that don't overlap in spectrum. This is a spread spectrum application. And to get the maximum performance in an infrastructure network, you try to use the 3 channels that are mutually non-overlapping. Fancy word for saying the 3 channels that don't overlap each other in spectrum space. And I'll have a spectrum shot in the next slide. And you lay them out in just a cellular pattern. As I mentioned towards the end of the class last time, that looks great on a flat graph. Makes perfect sense. Oh, fine, we just lay out this little grid. Except that these things don't radiate, and we don't live in a flat world. We live in a world that has 3 dimensions. And so if I mount an AP on the ceiling in this room, its signal is going to penetrate upstairs, and it's going to penetrate downstairs. Can you limit that? Yeah. Is it feasible to do so all the time? No, and not even most of the time. So what we're going to have to start doing is thinking about these things radiating in 3 dimensions. That's actually where we're heading with the design. For today, I am going to consider a flat world. Okay, we're going to start doing some of these design exercises. This is actually the only day we're going to spend the entire time on it. But as we start doing these, we're going to start considering 3 dimensions in what we look at. I had asked you to consider one of our new dorms here. These are U-shaped buildings. They have, I don't know, 100 people on the floor, roughly, spread around 3 sides. We have to provide wireless access because that's something students expect, and users in any infrastructure now expect to be able to walk in with the user device and get 802.11. How you do that is not just geography, although geography is important. The other thing you have to remember is that these devices, access points, are bridges. Bridges in the layer 2 sense of the word. We are connecting an air interface that has an over-the-air protocol that we use. We are taking those frames, disassembling them partially, and then reframing them for a wired backbone. Gigabit Ethernet in most cases. That means that each of those APs has a processing load just handling traffic. Okay, so it's not just like here's a radio and we can do everything we need. We've got to consider the processing load. We are using CSMA-CA. We've talked about what the algorithm does. So that AP is also managing all of the communication on that air interface. It is the authority for transmission. So there's a processing load associated with that. Current APs, and we're not going to, for now, I'm going to note this and then we're going to set it aside for a little while. Current APs also are capable of representing more than one network simultaneously. In other words, a single physical radio system will support more than one BSS on its air interface. Put another way, I can have one AP that will host multiple logical networks simultaneously. And you see this on campus. You've got MSU student, you've got MSU guest, and you've got MSU employee. Those aren't separate APs. They're all hosted off the same hardware. There's a processing load involved with that. Why am I beating so hard on processing load? Because this is the other side of the design coin. And to a certain extent, it fights with geography. And that's what we're going to focus on today, as a matter of fact. That processing load limits the number of simultaneous users you can support. Now, it's a soft limit. It's not like, you get, it's usually somewhere between 20 and 30 is the rule of thumb that you're given. It's a soft limit. It's not like if you go from 25 to 26, everything stops working. But this is a statistical access system. So the more users I load on this, the more I increase the processing load per frame, the more I have to think about everything I do, and the more I have to divide, me, the AP, have to divide my processing power and all of my resources. So 20 to 30 is the rule. We're going to use 25 today just because it keeps the math easy. Why that gets important is we have to consider that when we look at coverage. Now, coverage is a word that we throw around a lot, but we're going to have to put some limits on it. What I'm going to have you look at today are 2 aspects of this. You are in a transitional world on this. We're moving from a world where 2.4 gigahertz is generally what's used to a world where the 5.5, 6, and 7 gigahertz, we're going to use 5.7 today, are more and more commonly used. What's the advantage? At 5.7 gigahertz, the channels don't overlap, and there are a lot more of them. So we've got elbow room. Also, we can support something called channel bonding, which we'll talk about later, but it lets you use wider channels. Wider channels mean what for throughput? Data throughput. Got more spectrum space, I can move more data across the link in a given amount of time. So these are faster links. Okay? And that's what the trend that everybody wants is. You don't like sitting and waiting on anything better than anybody else. So that's where we're moving. So what I want to work on today is kind of pull some of these things we've talked about over the semester into just a design framework, just things you need to consider, okay? So with that in mind, let me show you this as a reference, and then I'm going to give you a sheet we're going to spend the rest of the time in here kind of talking through question at a time. For this project, a single AP can handle about 25 users simultaneously. That's actually a pretty good rule of thumb just to keep in your head. It's kind of right in the middle of that range. If you are doing critical infrastructure, you need to dig into that number very carefully, reading the specs for your user gear. Whatever, if you're using Cisco, if you're using Adtran, if you're using Ubiquity Networks, whose ever stuff, you want to read into that rule pretty closely. And it's sometimes hard to find. No, it's not sometimes hard to find. It is hard to find. They don't like to write it out because it doesn't look good. I'm going to pay you $400 or $500 for this, and you're going to let me support 20 or 30 users. I've got an auditorium with 300 seats. Okay, those are the kind of problems we start getting into. So you're going to have to dig to look for this. Second, here is, and we looked at a variation on this slide that showed the worldwide allocation. Remember, there are actually 14 channels in this spectrum space that are defined. We can only use 11 of them. We're not allowed to use 12, 13, or 14 in the United States, or most of North America for that matter. Only Japan allows use of channel 14, which if you go back and look, 14 is the only one that is completely non-overlapping with 1, 6, and 11. So the bottom line is pretty much any part of the world where you're standing, this is what you have to work with. You may have another channel that overlaps slightly, only slightly up here, but you've really only got 3 non-overlapping channels, which means you're limited to maximum performance only using a design pattern, a cellular pattern of 3 frequencies. Can I use the others? Sure. I can use 1, 6, and 11, and then I can put, I don't even know what channel it is, 24, 27 would be channel 4. I can put channel 4 in. Now the problem is channel 4 partially overlaps with 6, and it partially overlaps with 1. Is it terrible? No, but you've got more users in the same spectrum space. That's going to look like noise to the users on the other channel, on the overlapping channel. So it's better if you don't have to do that. Okay. We're going to assume you're not going to do it, because for infrastructure networks, that's really not a good way to solve problems. Sometimes you can't avoid it. It's not the best way to do things. The other one, this is the 5 gigahertz, the uni bands. We'll dig into this a little more when we start looking at some future design problems, but basically this is subdivided into 4 pieces. You have the lower frequency channels are limited in power, and they are for indoor use only. You're not allowed to use them outside because they're protecting radar installations and things like that. The upper frequency bands, and I'm purposely being vague about where the boundaries of those are for right now. I don't want you worrying about it today. The upper frequency bands are allowed to be used indoors or outdoors. Depending on which ones of those channels you choose, you may have a power limit of 250 milliwatts or up to a watt of power. We'll talk about that later. But notice what's going on with the channels. These are non-overlapping. So it's a lot easier for me to build an infrastructure. Okay, so why don't we all use this? Well, the commercial reason is until fairly recently, it wasn't easy to build equipment that used these at the consumer level. It was expensive. It was not particularly reliable. We've gotten much, much better at doing this in the last 10 years, particularly the last 6 years. So this is now a feasible way to do things, and we can plan on it. Okay, whoops. I didn't mean to do that. What I meant to do was this. Find where I put down my papers. There they are. So what we're going to do, and I would ask you not to work ahead of me on this, because I want to use this exercise as a discussion, the core of a discussion. So if you will, go ahead and calculate out. Oh, did I give you two? Yeah. Go ahead and calculate out the first two. Take, you can work in pairs if you don't have a calculator or whatever. Let's take a couple of minutes, and I want you to work through the first two. Sound familiar? Yeah, I had this as an exercise problem lots of times. What are the variables when you're calculating free space path loss? Frequency and distance. Exactly right. Anybody need a reminder on the equation? Okay. Loss, free space, isotropic, 36.58 as a constant, plus, what's the first term? 20 log of frequency, plus 20 log of distance. What are our terms here? Frequency is in megahertz. Distance is in miles. Okay. Notice what I've given you for assumptions. I've given you the 2.4 and 5.7 gigahertz, so you're going to have to convert gigahertz to megahertz. What do? Multiply by 1,000. Move the decimal 3 places to the right. I have to wave. I literally don't know right from left. I nearly flunked my driver's test because of that. So almost every time I say right, my wife teases me. I'll say, turn right, and I shake my right hand because I'm making sure that this is right. You know, this is my right, W-R-I-T-E, hand, and this is my not right hand. Distance is in miles. So we're getting kind of an interesting situation here. You're actually calculating the log of something that is less than 1, which means what? It's going to be a negative number, right? So in other words, this is actually going to be 36.58 plus whatever this term is, plus a negative number. Okay, in other words, you're going to subtract it out. And 300 feet, which is typically what we assume for the coverage area of an access point. That's kind of what the protocol descriptions and all talk about is about a 300-foot distance, so a radius of 300 feet. 300 feet is about 0.06 miles. Log? It's the logarithm to the base 10. Well, you calculate it. It is, if you're going to, what you're saying is I'm going to take 10 and I'm going to raise it to some exponent to equal a number. In this case, if I have, what did I say for frequency? 5765, for example. I'm going to calculate the number that if I take the base 10 and raise it to that exponent, the answer is 5765. That's what I'm calculating with logs. LOG is base 10. With a slide rule. So, do you know how to use that one? Yeah. Okay, yeah, you want to use that one. LN, just to be doubly safe here, LN is natural logarithm. It's a different base. It's not base 10. We don't use it in this class. I don't know of anybody that uses it directly in TSM. You can use it to calculate log base 10. I don't remember how. So we'll go through this. Actually, I want to do the other one first. So what do you end up with here? 20 times within the rounding, the way I punch it in, that's fine. So, okay. And then on the 5.8, I have the same equation, 36.58, 20 log F, 20 log D. Oops, I did this wrong. My bad. I looked too far up. Minus 24.44. So I looked over. Okay, do you agree? Do you get something pretty close to those? Okay. So let's put this in perspective. Typically, for 802.11 systems, you're talking about providing coverage over a radius from a centrally mounted AP, assuming an Omni antenna for now, over a radius of about 300 feet. So a circle 600 feet in diameter. Okay. What I had you do is calculate the path loss at approximately mid-band for the two different frequency ranges we'll use. So, same constant, of course, because we're using free space. Same distance, because we're talking about LAN access, about 300 feet. So the only thing that's changed here is frequency. Talk to me about received signal as related to frequency. Yeah, loss goes up as frequency goes up. Now, specifically, between these two mid-band frequencies, how much difference do we have in received signal level? Because that's what we're talking about. If I start with the same signal on this end, same power level at each of these two frequencies, my higher frequency signal is going to decay faster. Okay, so how much difference are we talking about? Yeah, 7.5. Call it 8, just to keep our math easy. So what's 8 in terms of fractions of the original signal, roughly? 3 dBs, how much? 3 dBs a half. So 6 dB would be a quarter of the original signal We're 2/3 of the way to 9 dB on a logarithmic scale. So we're 1/6 to 1/8 of the signal level just because we changed frequencies. Now, I'm not doing this because in 802.11 network design, you're going to actually work through this calculation. I'm doing it to point out this difference. There's a lot of advantage to moving to these higher frequencies. We have more non-overlapping channels, all of that. The problem is we have a lot more path loss. Okay? So we have to be aware of that when we're building our network. Now, as we dig into the protocols, what we're going to see is our protocols have actually gotten pretty good at dealing with this through some inventive engineering. But you still can't escape the physics. At the higher frequency range we have a lot higher loss. We're going to have about 6 times, roughly, 1/6 of the signal left on that frequency as compared to this one for the same amount of starting power. Okay, that's the reason I had you walk through that whole problem. Okay, so that's 1, 2, and 3. Now, here's what I've laid out for you. For today, we're going to discuss covering an area 600 feet wide by 1,800 feet long. Yeah, I wore a jacket today. It's cold in here. 1,800 feet long at both of those frequencies. Now further, so let's talk about physical coverage. How many APs do we need to cover that at those 2 frequencies? Assuming that under the protocol, it's a little bit of a trick question. How many APs do I need to cover it at 2.4 gigahertz? Yeah. What's the coverage area of an AP? Roughly for full specs. Spec plans around 300 feet of radius. Okay. So we can cover 1,800 feet by 600 feet with 3 APs. Okay. At 5.7, again, how many APs? We're still talking about 3 because we're still talking about systems designed to cover 300 feet. That's one of the mistakes people make is, oh, at the higher frequency, I've got to use a different AP. No, you don't. You still plan on about 300 feet. That's where you want to read the specs carefully, but you still plan. So if we're just covering the geography, we've got 3 APs. Okay? That's the easy way to look at it, and it is one way we have to. Flip the page over. And I had specified that there are 150 users in this area that we have to service simultaneously. Now how many APs do I need? I'm sorry? At least? So at least 6, right? Because I can handle 25 users per AP. Okay, so now I've got 2 answers. I can do 3 APs, or I can do 6 APs. Now, I've made it a little bit of a perfect problem because I've said the users are all evenly distributed, which usually doesn't happen. And as we complicate this problem, we'll consider that. Okay. The other thing, notice we're doing is we're assuming one size signal. We're assuming that 300-foot radius for this. Okay. We'll come back and visit that assumption a little later. Take a minute and just considering the geography, what channels would you choose for those APs at 2.4 gigahertz? Let's do that first. And what order would you put them in? Tell you what, take a couple of minutes, pair off, and discuss this between yourselves. And what I want you to come back to me with is for the 2.4 gigahertz spectrum, what channels would you assign and what order would you put them in?
We're using 3 or 6.
2.4 to cover the geography.
How many APs are we using? The 3 or
We're covering the I'm purposely not answering your question. To just cover the geography. I know I'm ticking you off. It's my job. To just cover the geography, how many APs do we need? Just 3 to cover the geography. Okay. And a 2.4 gig, how many non-overlapping frequencies do we have? 3. Okay. Now, so does it matter what order I put them in? Not a bit. 1, 6, and 11 in any order you want to put them up there. Now do it for users. To provide simultaneous coverage for 150 users.
6, 11, 1, and 11. 6.
Yeah. For geography, we only need 3, and it's no problem. We do 1, we do 6, we do 11. Geography's covered.
And we're still playing with 2 different frequencies.
Yeah. So for geography, let me draw these up here. So for geography in this, basically we're doing something that looks like this. 1, 6, 11. I realize I haven't shown any overlap. We're playing kind of fast and loose with this today. And it doesn't matter what order I put the channels in. I'm not going to have a co-channel adjacency in this design, which is a fancy way of saying I'm not going to have 2 systems running on the same channel right next door to each other. Remember, that's the goal we're after if we go back and look at how we do this. Here's basically what we built. 1, 6, and 11. And notice I've just got that repeating pattern. 1, 11, 6, 1, 11, 6. I've just got this repeating pattern of 3 frequencies. That's how we design these. For this geography, I've given you a very special case where it really doesn't matter what order I put things in. Now what I'm asking you is using that same area but with 150 users. Now what do I need to do? Okay, so what would I do? I've got 3 colors, there we go. Okay, so I'd do, what do you want to do first? 1, okay? So I'd do 1. Then, okay, and I know I'm not making, let me go back and do this better. I should have remembered my lack of artistic ability. My son got all of that. My sons, I should say, got all of that. Okay. Now what do I do? Just start over. Exactly right. My goal here is to not have systems operating on the same frequency immediately adjacent to each other. And I've accomplished that. Okay. Now, from the point of view of maintaining my network, I need to keep track of this. Now, I know that sounds like a piercing glimpse into the obvious, so I can keep up with it. Okay, we've got 300 APs on campus, thereabouts, 250 to 300, somewhere in that line. I'm not going to remember where all those are assigned, so you need to keep your records up. There's the, the hot tip for the morning. What happens if I want to expand this way? Still talking about a flat world. Okay. What happens if I want to expand this down this way? What am I going to put here? 11. Why? Because I've got 1 and 6 immediately adjacent. What am I going to put here? 1. Yeah, you see what's happening? I'm getting back to this pattern. Okay. That's the way you have to look at this. Okay. Now, when we do this at 5 gigahertz, what changes? Assuming everything meets spec so that they can do a 300-foot radius, what changes? Yeah, I don't have the only thing that changes. What would I do here? 3 channels, non-overlapping, right? The only difference down here is I don't even have to worry about this pattern if I don't want to. I can use more non-overlapping channels because more of them exist at the 5 gigahertz range. Now let's talk about expanding this to a broader area, which is going to be the easier pattern. One with 3 frequencies or one with 5 or 6 or 7 frequencies. It's going to be easier if I have more frequencies to put over more geography. Okay. So in other words, when you start looking at this kind of solution, you need to be thinking where you're going in the future. So what we're going to talk about as we look through this and as we look at protocols. First off, we're going to look at what are called repeating patterns, the cellular patterns, and we're going to look at the effect of the number of channels we can use. Okay. The next thing we're going to look at is how do we manage this when our users are not evenly distributed. Okay. Let me throw a simple problem that everybody runs into, and it's the one I started at the beginning of class. What if I have something like an auditorium? We've got an auditorium that seats 240 people down here. Using rules of thumb, how many APs do I need in that auditorium? 240. Yeah. I need 10 APs. Think about that at 2.4 gig. How do I control it? Can I do it? Absolutely. But what do I have to do to the coverage area of each AP? I have to make it very small. Otherwise, I'm going to bump into the other. The whole point on this system is not just throwing APs up in there, because we've been trained to think that more power is better. You know, by golly, if we can do 500 milliwatts, we're going to do 500 milliwatts. A watt's always better. No. If I'm trying to provide coverage for a lot of users in a very small area, what I want to do is very carefully control the radius of coverage. Okay. So what I'm going to do is reduce my power to where I keep that radius of coverage only over approximately 25 people. Now, would I really do this in an auditorium? No, because your world gets more complicated. I'm saying simultaneous users, and that assumption means that all of those users are using this network fully all of the time, meaning every second. That's not the way it works usually. So there are more dynamics going on in this, but you see where I'm going with that. If you have a lot of people in a relatively small area, I've got to be very careful about how I design coverage. I've got to look at both geographic coverage, and I've got to look at the number of users. I'll give you a perfect example. When Lamar Balcom comes up, one of the things we're going to ask him about is the CFSB Center, our arena. Think of the situation you have in there. What do you think's happening